PhD from University of Michigan. And her research is some by studying heavy ions in solid wind and transit. She simulates the non-equilibrium and emission and recombination processes translate to investigate the thermodynamic conditions that will produce ion accumulation and displacements. In the meantime, she is also part of the solid heavy ion sensor team and absolute probe suite team. And let's welcome Yeimy and thanks her for.
So I figure because there are people online, maybe I can point with my pointer if that works for people. Okay. So yes, thank you for the introduction. So today I wanted to share some work that was recently published as yesterday actually. I can share the link to the paper if people are interested for the talk, or you can email me. But yes, so today I wanted to talk about time-dependent ionization. So looking at the evolution of heavy ions within evolving structures of the mass ejection. So we've tried to recreate with the predictive sciences for their mass model. We tried to reconstruct some of the charge states in connection to the CME from observations from these swings at L1. So those are particle observations of heavy ions. And so this I put right in the title slide. This is a synthetic intensity, a movie of the EUV synthetic intensity just coming from the MHD model, which is really cool, but I'm not going to talk about it, so I thought I would just put it right on the slide. So as I was saying before, so we're trying to reconstruct the coronal mass ejection using this MHD model. So I think most of us in the room are pretty familiar with what a coronal mass ejection is. So one of the things that I wanted to point out about coronal mass ejections with this slide is that oftentimes, during the sort of large-scale reconnection event that releases all this plasma magnetic flux into the fluid sphere. So it's not just a homogeneous plasma blob that gets ejected. We often see it in this multi-part structure. So trying to point out some of the different structure that we see in white light coronagraphs. So you can see the edge, the cavity, and the filament is very bright from the core that we often see. If you're sort of looking at it in the right direction. Well, so the leading edge forms as the plasma gets ejected and accelerates to this slower moving coronal plasma. So you get this huge compression at the front, density enhancement. Generally, a cavity is much less dense just behind the leading edge, and you get very bright, dense filament form. And so what I wanted to point out is that these different structures can be markedly different in the coronal structure. So the leading edge and cavity plasma, as I pointed out here, can be, so typical coronal conditions, so multi-million temperature plasma, fairly tenuous compared to the typical core at least. And so here we're expecting to see very highly ionized plasma, as you typically see in the solar wind. And in the field of intelligence, the audio is not very good. Yeah. Well, maybe even watch like that. It's try to make your life. Okay. Can you hear me, or should I speak up? Okay. Yes. Yes. So the leading edge and the cavity part of the CME that we often see in the white light coronagraphs, those are going to be fairly ionized, typical coronoplasma. While the filament core, so the filament prominence, which is often called when it's seen on the disc and then on the limb, it's given two different. It's the same structure, but given two different names. So that really dense structure there is typically several orders of magnitude cooler and denser compared to typical coronal conditions. So cool, in fact, that we often see that it's often composed of very low ionized plasma, even neutral sometimes. You can see it, and it's just hanging out in the corona. So these are two images in the EUV of the prominent structure sort of magnetically suspended within the corona, and you see these blobs, these dark blobs in the UV that are essentially absorbing UV radiation, but also not emitting in that wavelength because they're very cool, dense structures. And so one of the things that you see very quickly as the coronal mass ejection starts to erupt and lift off of the sun is that one of the ways in where you can see that there's very rapid heating happening immediately after liftoff is that the structure, the prominence itself, goes from this absorption feature into emission feature. So I don't have a movie of that. There's actually one that I presented during my thesis, which is really cool, but I couldn't find it. You can see the transition of this dark blob into emission in the UV, meaning that there's very rapid ionization taking place. And now the structure itself is emitting in the UV in very similar conditions to coronal plasma. And so really at the heart of trying to figure out what is rapidly heating and accelerating the plasma out of the corona is really during these early stages of evolution. So during the initial liftoff and evolution of the plasma out of the corona, which is often why, so we can really try to examine what's heating and accelerating the plasma by looking at individual events. And sort of studying these events, which have been observed very well, both remotely and from the perspective of in situ observations, and kind of linking those together, which is exactly why we've chosen the Bastille Day CME as an example. So the Bastille Day, I put here a video of the eruption. So it erupted on July 14th, 23 years ago, so during peak solar maximum, solar cycle 23, in the year 2000. So it was driven by a filament eruption. So you can actually see it in the movie. So when it restarts just north of the center, it was driven by this filament eruption. It's a halo CME directed straight to the Earth. It was associated with a very energetic X-class flare. So the classification of flares they're classified as the peak soft X-ray emission of the flare. So there's A, B, C, M, and X, X being the highest classification of flares, a very, very energetic event. And you can also see the energetic particles being the detector just after the eruption. So the leading edge of the coronal mass ejection in the coronagraph was clocked at roughly about 1,700 kilometers per second. That's very, very fast. So I put here that the mean speed of a typical CME is roughly between, so looking at a whole solar cycle with CMEs is roughly between 400 and 500, 600 kilometers per second. So this is a very, very energetic and fast coronal mass ejection. And so like I was saying before, this is a very, very well observed event from the perspective of the CME itself, so the flare, its geoeffectiveness, its sort of the disruption of the heliosphere. So there's been 34 peer-reviewed articles associated with just Bastille Day itself. So we're actually number 35. So we just published, and I know of another group that's also working on looking at sort of the energetics of the flare from the mass model. So a lot of papers written about Bastille Day because it was such a cool observed. Yeah.
When you see this portal, is that for the range of data?
So from like the coronagraph, so there is a velocity, right? So there is sort of an acceleration profile. Most of it happens. There is in asymptotic speed, they probably reach within the C3 field of view, for instance. But I think the velocity that's coded here, I'm actually not sure now that you mentioned that.
The reason I ask is that that's also not a sort of speed. Okay. So it's quite fast for the two speed. So it makes sense.
Yeah, that's a good question. I actually don't know exactly where this is. Yeah, so 1,700 kilometers per second, probably somewhere between C2 and C3. From the in situ side of things, there was some deceleration. So the velocity that was measured by ACE was just over 1,000 kilometers per second. So some deceleration, I guess, between the Corona and here. But that's a really good question. Yeah.
Yeah, like 3 to 4 out there. Right.
Oh, sure. So the simulation did get up that high. I think 2,000 kilometers per second, and there was actually a time altitude stamp. If we just scroll forward, we can see it. So now I'm very curious. So not to spoil anything, but so the 2,000, right? So just below, so about over 1 solar year from the surface. So if we believe the simulation.
That's the big
Yeah. But it was able to capture. It's really tremendous. Okay, so this is from then the perspective of the in situ observations, like I was saying. So it was a halo CME. It just north of the center, is perfectly sort of directed towards the Earth. It reached Earth roughly about a day because it was traveling so quickly. After 5 successive CMEs, so we saw 5 CMEs. It was peak solar maximum, and then we saw this 1,000 kilometer per second coronal mass ejections reach ACE. So the Bastille day, according to the Richardson and Kane ICME list, is within the boundaries of these of the red vertical lines. So these are observations. The first 5 panels are composition, because that's mainly what I do. First 5, and we'll be focusing on these 3, so I'll come back to these. Bulk properties, right? Temperature, bulk speed, density, and then the magnetic field at the bottom. So just in case some of you are not familiar with looking at charge state distributions, so here, so this is a charge relative abundances of carbon, oxygen, and iron. So the way that you read these are, so each timestamp is associated with a full charge state distribution, where this is, for instance, carbon 4+, carbon 5+, 6+, and then the same for oxygen and iron here. So the CME, we can see from the magnetic field, large fluctuations in the magnetic field towards the beginning. This is the sheath part of the CME, so that's generally connected to the leading edge that we saw a couple slides ago. And then from the magnetic field components, we can see there's huge curvature in the magnetic field that was associated with flux growth. I believe there was a reconstruction of it. I don't remember who wrote the paper, but there was a reconstruction of it. And so the magnetic field components, it had southern, right, a negative EZ component that was ideal for data reconnection with the magnetosphere, Earth. It drove a huge geomagnetic storm. It's written up in this paper here. So like I was saying before, there's 34 peer-reviewed articles on the Bastille day, but yet there really hasn't been any work done in looking at the ionic composition, ionic structure of the Bastille day that we have from ACE. And so one of the reasons why we were really interested in looking at the heavy ions is because it could really tell you a lot about the early evolutions, the onset, the early stages of evolution
we don't have any plasma that would be like the shift region of this. Or what's this like?
Oh. So those are the lower resolution components from SweetCam.
Okay.
And there was no high. Yeah, there weren't. At least the one, not that I could find.
Okay.
Online. Yeah, unfortunately. And so, like I was saying, we're particularly interested in looking at the evolution of the heavy ions because they can tell us about the early evolution of the plasma. So, conditions of the plasma back in the corona. And the reason for that is because the ions and the charge states that we measure that we saw on the previous slide are a direct product of the ionization recombination processes happening during these early stages of radioevolution. And so what happens is that they undergo what's been called the Friesen process. So as we saw before, there's huge expansion that happens in the structure, in the coronal mass ejection early on in its evolution. That causes the density of the plasma to go down very, very quickly. And so as you get farther and farther away from the sun, the ionization recombination processes, which are directly related to the density and the temperature, of course, they become less and less effective as you get farther and farther away. The density is too low for any of that to be effective. And so what you end up with are ions that, or at least relative abundances in ion ratios that become fixed at a certain height away from the sun. And so this plot here, so this is from my 2019 paper, is a visual representation of the Friesen process for some of the carbon, oxygen, and iron ions. So how you sort of read this plot is we're looking at a ratio of the relative abundance of each ion divided by its frozen in value as a function of distance, heliocentric distance from the sun. So when this curve, essentially this particular ion profile gets to 1, that's when it has reached its Friesen altitude, right? That's when the ratio that you're looking at that distance is no longer changing. That
Friesen related to the plasma.
Yeah, exactly. Because the ionization and recombination are driven by collisions with planets. You have some ionization effects; these are pretty minor if you're just looking at solar wind. CME is a little bit more important, but generally collisions with electrons is what drives ionization and recombination. And so once your plasma becomes collisions, it's no longer happening. It can no longer happen at a time scale that's fast enough. And so one of the things that I wanted to point out here is that, so the charge states that we measure in the heliosphere from ACE are then undergoing this Friesen process. One of the things that you'll notice when you look at the different ions and the different elements is that each charge state really has its own evolution and its own Friesen altitude. And so it really does, depending on where it freezes in the evolution, it could really, when you look at the full distribution, it could really sample a large range of the evolution. In this case, this is a CME that was evolving at least in iron and oxygen and some of the carbon ions out to 14, 15 solar radii, which is very, very far away. And this is, for something like the solar wind, it generally tends to be closer to the sun, but for CMEs, it tends to evolve, the ions tend to evolve much faster, or much farther away from the sun, rather. And so what you end up with are these charge states that are directly reflective of the heating and cooling happening up to its freezing point. So in this case, up to 15 solar radii, you get the thermal dynamic evolution of the plasma really imprinted in the charge states that you measure anywhere in the heliosphere, right? After they've undergone that Friesen process, you can measure them anywhere in the heliosphere and they won't change, right? The relative abundances won't change. The absolute abundances, because plasma is expanding, density is getting lower, but the ion ratios, relative abundances themselves will be completely frozen into the plasma, which is great for us because then we can go and take a look at them, we can try to model them and reconstruct them, and get these very, very high thermal resolution constraints to the evolution of the solar wind or a CME in our case. And so for the Bastille CME, that's exactly what we've done. So within the 2 boxes that I put up there, so we've taken and we've tried to reconstruct the general structure of these 2 main structures of the Bastille. So the first half of the CME, generally showing very, very highly ionized plasma. So if you look at the torch state distribution of iron, the typical, so the plasma peaks at iron 16, and we see the presence of iron 24 plus persistently across this entire region. So highly, highly ionized plasma, as reflected by the torch state distribution of iron. The average iron torch state, which is a typical value that we use to characterize the ionization degree of plasma, is kind of oscillates between 16 or so. And just as a reference, down here is a plot of, I've taken an entire solar cycle worth of CMEs and plotted them up. And the typical average iron torch state of CMEs is below, generally below 13, I would say 14. So this is highly ionized plasma. And then the second half of the CME, so in that orange box, we see a very typical torch state distribution of iron, typical of CMEs. It's this bimodal feature in the iron distribution. We see a peak at iron 16, that's very typical, and then a peak at a lower torch state, which typically ranges between 8, 11, 12. And we'll talk about that. So we have this double peaked feature. And so I didn't mention this, but the first half of the CME, as we talked about before, the highly ionized materials associated with this flux rope that we were talking about before. And then the structure sort of towards the end is this double peak iron distribution. One of the things I'll also point out is that the iron distribution also contains these very low ionized ions in iron, but also in the carbon and oxygen distributions. That's very, very rarely in CMEs or the solar wind, really. And so we think that that's potentially coming from the prominence material, that prominence score that we saw in the first slide. And so
Where's that?
bottom plot, this plot down here.
Yeah. Where in the CME then?
Oh, this is actually for prominence material. So in the film, yes, exactly. So the work in 2019, it in a very similar way, but in not with a big and more sophisticated MHD model, we looked at a 1D evolution of different prominence, the prominence material, different structures of the CME to see what we try to match up the evolution of the torch states to a CME that we observed. So kind of in the same way.
It looks like you never reached level from the charge states don't they're inconsistent.
Oh, yes. So that's actually a really good point that I didn't bring up. We generally want to follow. So maybe a question would be, why don't we just look at the torch states and then compute a formation temperature and then get an electron temperature of the exact spot they froze in? That's actually a really good question because that only works if they froze in, they became fixed, have their under ionization equilibrium. Right? So that means that the charge states, if you were to go and look at the distribution, you'd be able to predict the electron temperature that formed that distribution. But they weren't in ionization equilibrium. And that's actually something that we talk about in the paper, where you actually have to follow the entire evolution up to their freeze-in point, because otherwise you really are blind to what the conditions of the plasma were at the freeze-in point.
That goes,
Yeah.
you know, Shiny had very nice questions. But I went to one with Ryan. So if we can show you we're showing leading material.
Yeah. So you can only really do that if you think the structure doesn't evolve, right? If it's just this kind of frozen into this particular structure in this particular shape, and it just expands out, and there's no evolution, then you get the sheath, the cavity, the prominence, all one fell swoop if you're right at the node of the CME. So if this was headed straight to us and Ace was sitting right here, then it would see everything in that order, right? I'm not sure if that's, I mean, we generally don't find the prominence.
Not all teams.
Yeah.
When they're measured, although.
I'm the wrong person to ask.
Angela, you know. Okay, is that in the cavity?
I mean, some people believe that the prominence itself lives in sort of flux strip that is that exists in the Coronal already, right? Maybe not Spira, but the prominence. But the way that it's modeled, right? When we look at I don't think I have the actual flux growth of the. Yeah,
So
that's a really pretty.
uh,
I mean, you could.
reactors.
Yeah. You're not sure what the leading edge is? I mean,
I'm sure
when
I
we,
know what it is.
you mean in this,
In a mouth pump.
yeah, in this.
Yeah. Something like in some the region between the leading edge and the filament for the yeah, that is related to structure.
So where there's leak material,
Sorry?
so that's where there's.
Well, that's where we see less material.
Yeah, that's
Does that mean
because
there's less?
yeah, when the field stress is strong
Yeah.
and we slow
Well,
back
that's
down.
just insecure.
Yeah, I mean, so I've been looking at the helium composition of CMEs with Parker. So we have roughly about probably 20 or 30 CMEs that we're looking at. What are the characteristics of the sheet? Is like you're saying, it's just compressed solar wind material, because when you look at the helium abundance, it's lower than the stuff after the sheet. And so I actually didn't realize that. I didn't realize that it could be just material from the solar wind in the corona that just gets swept out in it just kind of stays there. So when you look at the helium abundance, it is characteristically different than when you go deeper inside of.
Oh yeah, I mean it's ambient stuff. I don't know if it's leaking edge.
Yeah.
Parking like. I mean, you do sometimes. You need to look at. Some extent.
Yeah, so I have on the thermal side, like thermal helium, right? Not the energetic particles.
During the day. They get to
Maybe we should go to the similar, because people can hear you well, the mics are working very well. Like they can hear all the discussion. So I think it's better just to do like long discussion after the seminar to the line. But thank you very much for participating in the seminar.
So in relation to the sheath too, so I don't really talk too much about the elemental composition, which is kind of another element that would be kind of nice to connect to all of this. In this CME, at least you could see it dip down to photospheric composition, or much lower than the typical low-dip enhancement that you see in CMEs. So it's these blue curves essentially here. You see this big dip right at the sheath, and then it goes back up. So this is another CME here, which is really telling, right? So it seems to be material from another place, typically probably solar wind. Maybe. Okay, so for this work, the goal was to then take these two periods, these two characteristic periods that have this kind of signature in the iron. We're mostly focusing on the iron distribution. And so you can see them here. This is an average of the first half of the CME, and then an average of the second half of the CME, full charge state distributions, right? So it's just these guys here in a different view. And you can see the iron now very nicely peaking in iron 16, and then this double peak, sort of this bimodal feature in the iron. That's really nice. Again, not just in the Bastille day, but actually seen in most other CMEs as well, which is really interesting to us because we don't know how it's formed. So that was actually one of the structures that we were able to reconstruct as well. So the goals of the work is then examining these two periods, these two structures, to really understand sort of where they're coming from. So like you were saying, Tony, where is this structure that we're looking at? What does it relate to back at the sun? So this will help us, having a model that we can then connect from the corona to the heliosphere can help us then connect directly to the structure that was evolving that made these charge states. The conditions for determine the conditions that form these ions. So again, we're interested to see where does the heating and acceleration come from, and how does that relate to the ions that we measure, and then identify the energy source for the different structures. And so this is kind of a spoiler. One of the structures we weren't able to reconstruct, so the model does point to potentially some missing drivers of the ionization that could be connected to different energy sources. So like I was mentioning, we're working with the predictive science group. We're using their magnetohydrodynamic algorithm outside of a sphere, the mass MHD model. And so this was a model that was done for a different paper, so this 2016 and 2018 paper. So details of the MHD, the code itself, the MHD equations, the setup, and they had this very novel way of inserting the flux rope and actually letting it relax instead of having it immediately erupt. They actually drove an eruption, which is really interesting and very novel. So in a very high level, they had this pre-eruptive configuration of the flux rope. They drove the eruption through the coronal domain. They coupled that to the heliospheric domain because they were really interested to not only see what was happening in the corona, but actually linking it to the heliosphere observations, which is good for us because we were interested in that too. And so the paper itself did a pretty good job, the model itself did a pretty good job at reconstructing the morphology of the CME, and also through its simulated heliospheric propagation in connection to the bulk properties, did pretty well at and matching up with the magnetic field and some of the bulk properties, temperature, density, velocity. So on the left is the actual eruption. So this is the C2 Glasgow chronograph of the CME, and then on the right is the mass reconstructed chronograph image, and then this is in the EUV. Okay, I'll have to speed up. So generally, very good job at reconstructing the morphology of the CME eruption. It did quite well. So for our purposes, we've taken then the coronal solutions and we coupled the time-dependent ionization code, as I was mentioned before. We were really interested then in following the individual ion formation right along the different substructure of the CME and trying to link up. These are the observations that we see in situ. How do they link up to this evolution through the corona? by following the non-equilibrium ionization. So on the right is just the it's continuity equation that determines the ion population in your plasma. So we already talked about this, but the ionization recombination again is due to interactions with the electrons, ions colliding with electrons, recombining with electrons. So here the ions are sensitive to the electron density, the temperature, and then the bulk flow of the plasma is also really important. That determines how fast things are changing, how quickly sort of the plasma moves from one place to another, which is also really important to the ionization recombination. And then some of the model assumptions, we start with ionization equilibrium. We really don't know any better, so we have to start with ionization equilibrium at the boundary. We assume thermal equilibrium, so our electron temperature is equal to proton temperature. Maxwellian electron distribution, so the free electrons remain in Maxwellian distributions. All ions flow at the same speed, and then we're only considering the ionization from one transition to another, right? So carbon 5 to carbon 6, and vice versa. And so for the useful that the predictive science group did, they've implemented what are called these tracer particles in their simulation that have allowed us to identify the structure, use these tracer particles to sort of identify the structure they want to follow, and also in connection to thermodynamic evolution and the ionic evolution of that particular structure. So this is just a simulation of, for example, for the evolution that you're seeing on screen, this is for tracer particles associated with prominence material, essentially. So very cool structures, very dense structures at the sun. So we set the conditions that we were really interested in the particles that were actually flowing out of the simulation box. So those would be the particles that would be conceivably measured by something like ACE, right, a particle detector in the heliosphere making it out of the corona. And in this case, for instances or tracer particles that were prominence material that reached over 1 million Kelvin. And so what we can do is then look at the evolution of a single tracer particle, look at the conditions and evolution of them, and then look at essentially the simulated freeze-in charge states that we can compare to ACE. So here is just again, the chart, the relative abundances of carbon, oxygen, and iron, and then the associated temperature, density, and velocity of the tracer particle, that single tracer particle that we're following within the prominence material. And so in this case, I'll go over very quickly. As I was mentioning before, so we have these two structures that we were aiming to reconstruct. The second half of the CME was that bimodal distribution in the iron. So in this case, what we found is that for prominence material that gets heated up very, very quickly towards the beginning, within a couple of radii, and then begins to cool, this particular thermal evolution or thermal history of the plasma was able to reconstruct the bimodal distribution in the iron very well. And so what's happening is, so we kind of step through it, what we find is you have this prominence material, very cool, very dense at the sun, gets heated up very quickly and accelerates very quickly out of the corona, and the charge state distributions reflect the heating. And then what you get is ionization that happens up to iron 16. So iron 16 has a relatively large ionization potential, so it's very, very hard to take an electron from iron 16. The plasma then begins to cool, and so you don't ionize any further than iron 16, and then you get this cascade of recombination. And so you can see, especially from the iron distribution here on the bottom, you can see this recombination that happens, except iron 16 also has a very large time scale for recombination compared to its neighboring ions. So what you end up with is the recombination happening faster for the neighboring ions than it does for iron 16. And you end up with the distribution that looks like this. So a peak at iron 16 and then a peak at a lower value. And you get this bimodal distribution that we were seeing in the Bastille day. And very quickly, I'll mention, so we have a peak at iron 16, then you get another peak at a lower state. When we were surveying the evolution of different tracer particles, we found that the peak at a lower charge state is essentially governed by how long the plasma had to recombine. So the longer it had to recombine, the lower the charge state moved. The peak to the left happened. And so it was based on this freezing distance and the conditions of the plasma, of course. And so I'll just go through the second example very quickly. So same idea. In this case, what we're seeing is that we're trying to reconstruct the first half of the CME. So if you remember, that was where iron 6 had a peak at iron 16, very, very ionized plasma. And what we find is that the simulation really couldn't reconstruct the charge states the first half of the CME. This, as I sort of hinted at before, the mass model really doesn't get high enough to produce anything really above iron 16. So the temperature is much, much too low to form anything above iron 16. You really do need temperatures that reach over 60, which is something that we didn't see in the simulation. And this is typically the ionization stages that we see with something like the Bastille day. It's generally connected to flare sites, flare-heated material, some association of flares. That's generally where you typically find those conditions. So if we go back to some of the assumptions that we were talking about before in our model, so beyond the model not actually getting to the temperature needed to reproduce some of the most ionized charge states that we see, there's also the potential of non-thermal electrons contributing to the ionization in the plasma that is essentially not accounted for. If you remember, all the distributions of the electrons are fully Maxwellian, so we really don't account for any energetic electrons in the high energy tail. So especially for very energetic solar eruptions, X-class flare type events, we think that this is incredibly important to getting to the iron 24 plus that we saw in the observations. Another thing that we considered is photoionization. Photoionization can be very important for CME, especially if you have an X-class flare. But what we found was that it really didn't account for ionization beyond iron 16. So it's potentially very important to producing ions up to iron 16, but really not helping us in the sense of getting to anything above that. There's really not enough X-ray flux for that to be important. And so this is just, again, the prominence material and the hot flux stroke material in comparison to the observations. The simulations are in the blue and then the observations are in the black. So like we saw, the double peak distribution in the observations were captured fairly well with a mass model, but we didn't get nearly as ionized material as we saw in the observations. And so since I'm low on time, I won't talk about carbon and oxygen, but we can talk about that if people are interested. Those were also not reconstructed very well for what we think is a non-thermal effect. And so I'll end maybe on this slide. So what we're finding, so within the two structures that we're following, that we're tracking with the tracer particles, the heating experienced by those two plasma structures was due to field line conduction via the shock plasma at the CME front. And so there is this huge compression that dominates the frontals. So if you remember, the CME reached roughly about 2,000 kilometers per second in the low corona. And so very quickly exceeding the Alpine speed and forming a shock in the front. And you can see that in the 3 time steps that we've taken here, showing the ISO. This is the shock heating isosurfaces for the very, very high shock heating term, which are in the purple, and then the torch states of iron 16, so very, very ionized iron in the blue. So you can see the heating is essentially surrounding the outflowing material, and it persists for at least these time steps. So there's a lot of heating that happens in the front. That's generally where we see the highest shock. But the shock, if we look at the heating experienced by the actual structures themselves, so I plotted them here. So shock heating at the front. So we see actually a lot of adiabatic cooling in the two structures. That's combated by then our field line conduction that's coming from the neighboring structure, right? The shock plasma. It's actually heating the plasma right behind it, and you can see that from the formation of iron 16 kind of persisting and floating out of the material of the sun. Not a lot of radiative cooling and very, very little omic heating. So omic heating coming from heating directly from the current sheet. So that's something that we see that we thought was actually going to be really, really important for the CME. It turns out that it wasn't very important and not really influencing the outgoing plasma. So the omic heating is mainly confined to the sun, to the current sheet, right, that sort of remains in the sun. So localized to lower down, it really doesn't influence any of the torch states that are actually flowing out of the simulation. And so I'll skip that slide and jump to my summary. Like I was mentioning, we were able to reconstruct the bimodal feature in the iron distribution that we saw on the Bastille day very well. So this is coming through prominence material that gets rapidly heated and begins to cool. And we saw that cascade of recombination. We get the double peak distribution in iron that's reconstructed very well. We weren't able to reach any of the highest ionization states that we saw in the iron from the Bastille day observations. We think that, so again, photoionization doesn't seem to be important in this case. Potentially non-thermal electrons are responsible for this added and additional ionization that we see that really isn't considered in the model, but should be implemented and seems to be incredibly important for CMEs at least. And then the primary source of heating that we see for the two structures being field-aligned conduction, and that being, it seems to be incredibly important here for very energetic events. And then the slide that I skipped was the freezing distances. So when we look at the freezing distances of different ions in this case versus the case that we had before, that I was showing before in the 2019, very simple 1D model, they're actually very simple, which makes me very happy. Things are evolving out to 20 solar radii for iron cases, which is very similar to that 2019 paper, which is a much, much simpler model. And so I will end here and take any additional questions. Thanks.
Is there any question maybe on person then?
Yeah, you said that you didn't see photoionization wouldn't drive iron up to beyond iron 16 plus.
Yeah.
Was that just didn't see it in simulation, or is there some physical forbiddeness?
So the photoionization, right? So there needs to be high enough photon energy to ionize. Right, so there's a particular ionization potential that you need to threshold that you need to reach and go beyond in order to ionize iron 16. And so there is not enough energy in the X-ray flux that we see for that to happen. So yeah.
This is quite old, perhaps outdated, but both Stan Milwaukee and Rivera have tried to explain the higher iron charge that is given by moving. Maybe the polarization.
Iron 24 plus?
I don't think
Okay.
but this is it brings to words.
Yeah.
I don't know.
So we did
They did or not. I don't want to say for sure. There are higher triggers in the CSP that could be explained by the equilibrium tables of day.
Right. But we went through the exercise of actually calculating that, and we did find that it was, but maybe it'd be worth revisiting some of those papers.
It's a very basic question. What's the ionization?
Oh, I don't know. But I didn't mention this, but it's actually quite handy to look at the formation temperature for the relative components. So these are straight from Chianti. So for instance, this is, I didn't mention this plot, but these are the relative abundances of of the iron ions, for instance. Iron 16 is this curve right here, so it exists across a large range of electron temperatures. So it can kind of exist. Oh, okay. I don't know that. It's in the paper. Calculation.
Basic question.
So I will clarify. Photoionization seems to be incredibly important to everything, the formation of the ions below that. So it is important, we find. But it's just, so if we're looking at reconstructing a peak at iron 16, that's what we were in reference to that. It didn't seem to be. What's that? Iron 20, right? Yeah.
Well, also, I mean, it's something.
Yeah.
I think it's better to be.
Yeah. Yeah, so we were really concerned that they were not real. So Sue and I actually went through, looked at the energy per charge, and the difference, I guess energy per time of light mass per charge, and we were looking at them to make sure that we were actually seeing what we thought we were seeing. And she seems to be convinced. And I also talked to Jason Gilbert, actually bumped into him at AGU, and I was actually presenting on this. He was actually very happy that we actually chose this event because he also looked at G measurements and seems to be convinced that we're actually looking at iron performance. But that was actually a concern of ours.
Well, you can't get.
You don't often see it.
I mean, I think when you list, there definitely was.
Oh, wow. Yeah, I mean, it's very rare. This and the Halloween storm, I think, is the only times that I've ever seen charge states this high. Because iron 24 is really at the limit, right? You can't see much beyond that. So
I assume they could be not. I don't know the MHD model, but what you actually think is a very good CME. But I just want to before utility at any time because this is one of the biggest storms. So I don't think it is a Bastille event or the Everly storm. Those are the biggest extreme. Not more this make it stay more.
equilibrium. So that was you have to start with, you don't really know any better. You have to start with ionization equilibrium at the base, but after that it's a non-equilibrium. So it falls.
Be careful because MHD assumes some kind of equilibrium. Otherwise you get no linearity, which don't happen.
So the MHD is kind of independent of the coupled ionization. So this is more of a kinetic. We take the solution so that the only thing that is I guess in equilibrium, thermal equilibrium maybe, is the temperature, right? And we also assume, right, everything is Maxwellian, everything is kind of you kind of have to in MHD. Yeah, and so that's actually one of the things that we're pointing to as this isn't good enough to reconstruct the charge states that we see because the electrons can't. We know that they're not, and we can see them. We can see it reflected in the charge states because we just can't reconstruct them. But the ions themselves can flow and be a non, and that's the point.
I don't know that model, but from the equations that you here, you might say,
Well,
you know what you can do in your model, but you could actually take an extreme event,
Yeah.
and then you try to whereas take everything out of them.
Yeah.
So there is a gap for me. How you play
The MHD code has to be, right, like we were talking about, it has to be in equilibrium, right? In the thermal equilibrium in the sense that we're using that to then follow the evolution of the ions, but the ions themselves don't have to be in equilibrium because the changing conditions, so if you have a very steep gradient in temperature, density, and velocity, and in this case, you have very, very fast CME, you're pretty much going to be in that condition. I think it's pretty safe to say, and we do see that, which is why we need to follow. It's kind of going back to the question someone put up here. You can't just look at the charge states and then predict an electron temperature from that, because that's assuming what you just said, ionization equilibrium, which is we know is not the case, and we can see it from the charge states themselves. And so you do need to reconstruct the entire evolution of the ionization recombination history of those ions, which is what we're doing here.
go to the motor, not to the second extreme, and try to simulate the motor. If you don't have the intensity, then
That was for 2019 paper. So this is this paper here. So this is for an actual event. And we try to this is a very, very long. I think it's like 400 kilometers per second CME. And that's what we were attempting to do with this 2019 paper. So same methodology of the non-equilibrium ionization code, except in this case, not a Bastille day level event, just a typical CME. I think this is for a CME in 2005, so not during peak solar maximum, just a very sort of typical CME.
One last question. Well, I'll make one. Sorry?
Wait.
Sure.
Okay, so if I understand this correctly, we take that indice we put a flux rope and then let it fall through the 3D model that predicted sensitivity of that, and then at a certain point, we apply the model that includes the ionization rate. Is that what I'm saying?
Well, so they happen at the same
Oh,
place.
it's simultaneous.
Yeah.
Okay.
So we take these out to 20 solar radii, and that's also the domain in which we're applying the non-equilibrium ionization code. Right. So we're taking, they sort of did this on their own. They didn't include the non-equilibrium ionization code in this 2018 paper. But if you were to go and take a look at this paper, it sort of describes both this comparison, the remote sensing, and then also from the simulated passage at L1. And then that was their paper. They were trying to say this is a pretty good representation of Bastille data.
So that didn't include the ionization.
No, so this paper didn't. And so what we've done is then taken that simulation, we've taken the solutions for the coronal side. So everything in here, we know the temperature everywhere, we know the velocity, magnetic field components, although we didn't use magnetic field. And then we can use them to then couple to the non-equilibrium ionization. And then, so now you have the conditions for your plasma, you know how things are changing, so you can follow the evolution of individual ions that way. Because the ions, the reason why they're ionizing and recombining is because they're colliding with electrons. So you need to know what the electron temperature is, you need to know what the density is, and we know that because of the simulation. So the idea is then use those solutions and then apply it to the non-equilibrium ionization.
Just mention that you are we are using Maxwellian electrons, which I believe that thought it's even with CME stuff will come up.
Yeah.
I know that Quick Code did model capital for stamping. Saw a little bit of changes.
Yeah.
So what you're thinking is like for CME,
it needs to be. Maybe not in the commons material. It's very dense, very collisional. So maybe you can get away with it there, but it's not reproducing the observations very well for the flux rate material that we're talking about. So here is that's where we're saying this is very unrealistic. We know that they're not in Maxwellian distribution very early on. Layer conditions, right? There's papers showing that they're actually a huge contribution of non-thermal electrons there. And so we're saying this is something that needs to be included in future models because we're not being able to reproduce the charge states. We can reproduce the morphology as I showed before, maybe some of the bulk properties really well, but you're not capturing all the details that come from everything reflected in the charge states. Because these are really nice, right? They look like they're capturing the evolution quite nicely. But the details in the actual heating itself, all that stuff is kind of embedded in the charge state, and it's not doing a very good job.
Let's Frank that speaker again. Thank you everyone for coming. See you next week for another seminar which is going to be in person and